So hello everyone, my name is Quentin Bramas. I'm from the University of Strasbourg in France, and I will present this joint work with François Bonnet and Xavier Défago from Tokyo Tech. So about the topic we are considering today, it's about distributed ledger technologies, or just DLTs, and this includes all the different blockchains, but also Byzantine agreement protocols. And so the problem we have is we know it's really hard to analyze this wide variety of technologies. And so our first objective is to define an abstract model that encompasses all existing DLTs, but is descriptive enough to define properties and compare DLTs. So with our model, I will present the stateless property and see whether well-known DLTs verify this property or not. So first, what is a DLT? So it's a protocol that maintains a ledger, which is an append-only state. And this is done in a distributed manner by a set of nodes connected in a network, for instance. And so basically, the node in the network receive events, such as transactions, or it can be anything, and append data to the state, for instance with an append function. And for simplicity, we can first consider that the system is asynchronous, for instance. In a very abstract manner, we can consider that there is a function taking the current network, the current state, and a set of events, and creates from that a new state. We can consider that this is done every time the DLT appends data to the state. So the time slot corresponds to the time when a data is appended to the state. For instance, in the proof of stake blockchain, the nodes communicate together, and a node is elected depending on the node's stakes, and this node appends the received transaction into the blockchain. So given a DLT, its initial state, for instance it's the genesis block for blockchains, given a sequence of networks, given the sequence of events, we obtain an execution, so S0, S1, and so on. So that's how we model a DLT and the evolution of the states depending on the network and on the transaction received. So now we are ready to define the stateless property. So stateless means that a node can join the network without already knowing the current state. In other words, the current state can be verified using only the initial state. Okay. So when a node joins the network, each correct node in the current network sends the current state of the DLT. But malicious node can send arbitrary state. So a DLT is weakly stateless if one can deduce what is the current correct state of the DLT from all the received the local states. In other words, if there is a function taking all the received states, L1, L2, and so on, and returns the current state as T. A DLT is strongly stateless if, in addition to that, it cannot be fooled when receiving only a subset of the local states. For instance, if an adversary isolated the joining node and just sent malicious states. The property is probabilistic if the result of F is correct with high probability. With those definitions, we prove that Byzantine agreement protocols are strongly stateless, assuming that there is a fixed known set of nodes that participate to the agreement, and half of them that are correct. In a proof-of-work blockchain, such as Bitcoin, we prove that they are probabilistically stateless. And finally, we prove that proof-of-stake blockchains are not even weakly stateless. In future work, we plan to use and extend our model to define other properties. So if you have any question about this, I will be happy to discuss, and you can contact me by email. And thank you very much for your attention.